Yeah, so at the moment we are looking on random matrices. So we made the transition from vectors, random vectors, to random matrices, and also want to understand maybe concentration, in particular for the eigenvalues, and also what is the eigenvalue distribution in a meaningful regime. So the setting was the following. So I mean, we are talking about Wishart random matrices. So the setting is we have, let's say, we have data which are distributed according to a Gauss distribution. So X is distributed as a Gauss with mean 0 and a covariance matrix sigma in R to the P. And then we assume that we have n independent draws from this one. So we have n independent copies of such a vector. So we have x1 up to xn. Each of them is a vector in Rp. They are independent, and they have the distribution like this. Good, and then we are putting those guys into a matrix, a data matrix, and we want to understand the properties of this matrix. So X, capital X, is now the matrix where those vectors here are the columns. So we have n columns, n columns, and each has a length, is a vector of size p. So I'm putting here the first vector x1, then the vector x2, and then the vector xn. So what I get is a p times n matrix. Okay, and then maybe the important square matrix which we can form from this is the estimator for the covariance, which I call sigma hat, which is 1 over n, and then I take x transpose. Or if I want to write it in terms of those guys, it's the sum 1 over n, the sum k from 1 up to n, xk, xkt. So each vector gives me, I mean, this is a matrix, p times p matrix. So this is somehow the estimator for the covariance of my distribution. And I mean, the law of large numbers would tell me if n goes to infinity, p fixed, then this goes really to sigma. But that's not the regime we are interested in. Okay, but anyhow, so that's the matrix which we want to understand, and that's actually a Wishart matrix. Okay, and so, maybe let me write it down. So Wishart, statistician, who introduced random matrices exactly in such a context, for dealing with making estimates, or estimates for Gaussian distributions in high dimensions. Okay, good. Yeah, and now the first thing we looked at was what is the in principle, we are interested in the eigenvalues of this, and in particular, we want to understand concentration, so that maybe the eigenvalues also concentrate around the averaged value, and we want to understand the averaged value. Okay, but first we looked on the largest eigenvalue, and we tried to see whether we can, from what we know up to now, whether we can deal with this, in particular concentration. Can we also do concentration for the largest eigenvalue? And there, I mean, first of all, the largest eigenvalue of a matrix is really a Lipschitz function, a one Lipschitz function, which means we can use our concentration phenomena. So we know that we have concentration just by our Gaussian concentration for Lipschitz functions, but the problem is we don't know the expectation. That's usually the strange thing. I mean, we can show concentration often quite easily with our machinery in the background, and it tells us that things concentrate about the mean, but usually it's not so easy to calculate the mean, in particular for such nonlinear functions. For the norm of a random vector, I mean, this was quite easy, but for the eigenvalue of a random matrix, I mean, what is the mean? Okay, and so we tried to get a better understanding of this, and also develop tools for, let's say, see concentration more concretely in such instances. But the problem somehow is that we don't really have a very concrete formula for the eigenvalues. They are very nonlinear, but also not very explicit functions of the matrix entries. Okay, but last time I started to show you how we can address this question, and the point is that actually, I mean, we have a kind of course, we have a kind of formula, and yeah, So what I'm looking at is the operator norm. Of course, the largest eigenvalue, the largest eigenvalue of this guy is the norm of this, and this is connected to the norm of x. So what we really want to understand at the moment is the norm of x. Or you can also say this is the largest singular value of the matrix. Okay, so we have of course a kind of formula for the operator norm. By definition, it's the supremum or the maximum overlooking how much can we increase length by applying this matrix X. And so maybe I wrote it in the form, so it's a supremum, but it's achieved, so it's really a maximum over, let's say, V's in, where are we here? In R to the, let me first write down, so it's X, V, comma W. So X is a matrix which goes from R to the N to R to the P. So V is in R to the N and W is in R to the P, and they have lengths, both of them have lengths less than 1. I could also take equal to 1, but for our arguments maybe less or equal 1 was better, because the argument which we made was that this maximum over infinitely many possibilities can be replaced by a maximum over finitely many possibilities. So we have here a kind of formula for x. It's a maximum of quantities which we can control quite easily. This here is a linear thing essentially, or quadratic thing which we can control very easily, but we have to take the maximum and we have to take this over infinitely many guys. So even if we have concentration for each of them, if I have to take the maximum over infinitely many possibilities, this is not very helpful. So for each of them I have a small deviation, probability for a deviation, but if I have this for infinitely many, then the deviation can be everything. Okay, but the idea in such a context is that actually we can cover the space over which you have to take the maximum by an epsilon net, by a finite number of points which are closer than epsilon to any point, and then it's enough to control these quantities on this net. So what we showed last time is that actually I can replace this maximum over all the points in the balls by points from epsilon net. Okay, we have make a small mistake by this because we only approximate things. So I have here a factor 1 over 2 epsilon, which is coming because I'm only approximating guys from here, from points from my net. And now the maximum is running over elements from an epsilon net for R to the N and epsilon net for R to the P. So this means every point, for the ball. So every point here in the ball, in R to the N, I can approximate up to epsilon by some point from this net here, and the same here. Okay, and we also saw that we can control the size of such net. So this depends on epsilon. And so, for example, maybe in the following, I will choose epsilon is 1 over 4. So you see here, of course, I should not go bigger than 1/2. Okay, but 1 over 4 is good. Then I get here 1 minus 1/2. So here I get a factor 2. And the size of the n's, so this was a bound like, I don't know, 2 divided by epsilon plus 1 to the n. So in this case, this is 9 to the n. Or here it's 9 to the n and 9 to the p. So here I have, okay, I'm still missing, of course I have here the same thing as before, x, v, w, but now v and w are just coming from this finite set, and this finite set has a size which we know how it depends on the dimension. Okay, so I'm fixing epsilon in the following, and then the dimension of n, the size of n, is less than 9 to the n, and the size of m, the epsilon net for the ball in dimension p, is less than 9 to the p. Okay, so the size, of course, of those balls also grows exponentially in the dimension, but it's a finite number, and this exponential growth in the dimension is still good enough compared to the exponential concentration which we have for each of the guys. Good. Okay, but so let us check this out. So what we really can do with this. So I have this compared to this. And now I want concentration. I want concentration of this norm, which means I should say what are large sizes of this guy. So I want to have probabilities for the fact that x is, let's say, bigger than alpha. Okay. Yeah, and of course, by this estimate here, if x is bigger than alpha, because x is smaller than this guy here, then this means in this maximum must be bigger than alpha times this 1 minus 2 epsilon, and so at least one guy appearing here must have a bigger value. So this means if x is bigger than alpha, this means there must be at least one v and w from those nets such that their corresponding quantity is bigger than alpha modified with this guy here. So this must, so there is a v in my net in n dimensions and a w in my net for p dimensions, such that the quantity x, the matrix x, applied to the vector v, the inner product with w, is bigger than alpha times 1 minus 2 epsilon. Okay, and this is now a quantity which we can control. I mean, this side here is now a very easy function in the entries of x, for which we know concentration quite well. Okay, so namely, what is this? Or maybe first of all, so if we have this here, this allows us to reduce probabilities for this to probabilities for this. So namely, if this guy here is bigger than alpha, then it must be in one of those sets for which this happens, so it must be in a union of those sets. So this means, I mean, the situation where the norm of x is bigger than alpha is contained in the union of the sets here running over my nets of the sets where this x, v, w is bigger than alpha 1 minus 2 epsilon. Okay, but now what I want is an estimate for the probability of this, that I can estimate it against something from above, and the probability of this is of course the probability of the union, but the probability of the union can be estimated against the sum of the probabilities. So this means that the probability that the norm of x is bigger than alpha is smaller than the probability of this union, which is smaller than the sum of the probabilities over my nets, v in this net n and w in m, and then I have here the probability that this essentially quadratic form in the matrix X is bigger than alpha times 1 minus 2 epsilon. Okay, and now for those here, for those we have our concentration. So namely, let us see what we can say about this. So namely, what is this X, V, W? Of course, I mean, this is the matrix. I mean, the matrix X has the entries Xij. That's our independent Gaussians. That's the guy which we know. And here I apply this to V and then inner product with W. And of course, this is just a quadratic form where I'm taking the sum over the indices. So I'm taking the entries of the X, multiply them with the vector Vj. So this is the matrix product X applied to V, and then I take the inner product with W, which gives Wi. So the Vj's are the entries of the vector V, Wi's are the entries of the vector V, and the Xij are the entries of the matrix. And I'm summing here, of course, over I from 1 to P and J from 1 to N. And those guys here, the Xij, that's our random elements. They are all distributed like standard Gaussians, and they are independent. Yeah, and so what I have here is now just a sum of independent Gaussians with some coefficients. And I mean, we know what is the, I mean, okay, we know that the sum of independent Gaussians is again Gaussian. And how do we, I mean, of course, everything is centered, so the mean is 0. So the only information is the variance. And what is the variance of the sum of independent guys? That's just the sum of the variances. So that's just, I mean, so the variance of xij is 1. It's getting multiplied with those numbers. So the variance of those whole thing is multiplied with this, the square of this. So the variance of each of them is those guys squared, and we are summing over everything. So this means, yeah, so this whole thing here, this is a Gauss distribution because it's the sum of independent Gaussians, and it has a variance sigma squared, which is given by summing all the variances of all the summands which I have in this sum. But I have, of course, the sum consists of all the terms where I is running from 1 to p, and j is running from 1 up to n. And then the variance of this individual term is just vj squared times wi squared. Okay, and now we see that what I'm doing here is I'm summing the vj squared over the j's, and I'm summing the wi squared over the I. But this means, if I sum those guys, I'm getting just the norm of those vectors. So the sum over the j gives me just the square of the norm of the vector v, and the sum over the I, over the wi squared, gives me just the square of the norm of w. Yeah, but I mean, my net was in a unit ball, so the norms of those guys are less than 1. So what I have here is, yeah, something which is less than 1. So I get here a Gauss distribution which has norm less than 1. Yeah, okay, and of course we know what is the probability of a Gauss being bigger than alpha if I know the Gauss has a given variance. So for each of those guys, I have had the probability that this quadratic form here, x, v, w, for each fixed v and w, that this is bigger than alpha. This is just the tail of the Gauss, or I mean, integrating the tail of the Gauss, but we know that we can also estimate this against 1/2 e to the minus alpha squared over 2. And here I would have the sigma squared. Of course, it depends on sigma, but sigma squared is less than 1. So I can estimate it like this. So I mean, each of those guys has a kind of concentration in this usual form. Okay, and now, yeah, now let us go over again, go back to this essentially, so we can estimate the operator norm in which we are interested, the deviation for the operator norm against the probabilities for this. But instead of alpha, I have here alpha 1 minus 2 epsilon. So maybe let us use this. So I replace now alpha by alpha is 1 minus 2 epsilon. And now maybe I really use the explicit value, epsilon equal to 1 over 4, so that I also have something concrete about the sizes of my nets. Then this is 1/2 alpha for epsilon is 1/4. And so the probability that this xvw, this inner product, is bigger than 1 over 2 can be estimated by 1/2 e to the minus alpha squared over 8. Because I replaced alpha squared by 1/2 alpha squared. Okay, good. Yeah, and now this probability is less than the sum over all those probabilities. Each of them, for each VW, I have estimated in the same way by this factor. So for this, I just have to multiply with how many summands I have here. Yeah, and this gives me then more or less my final result for estimating the probability that the norm of my matrix is bigger than alpha. So this can be estimated against the size of the net n, so the number of elements in this net n, times the number of elements in the net m. So this is for the sum over the w's, and each of them gives me a 1/2 e to the minus alpha squared over 8. Okay, and this here, okay, I have the 1/2, and the size of n for this choice of epsilon is less than 9 to the n, and for m it's less than 9 to the p, and then I have e to the minus alpha squared divided by 8. Okay, and I think we agree that we should write all exponential guys in terms of e, not in terms of 9. So let me just estimate 9 against e to some power, and 9 is less than e to the power 3. So let me just, okay, so 9 is less than e to the 3, so I just estimate this against e to the 3, and then I have here less than 1/2, and then I have e to the, so this here is less than e to the 3n, this here is less than e to the 3p minus e to the minus alpha squared over 8. Okay, or maybe just put out the minus 1 over 8 and then see how the deviation compares to the dimension. Of course, that's something which we want to see. I mean, the deviation should be somehow small compared to the dimension. Of course, we have here something which grows in the dimension, but the deviation should be compared to this. Of course, I mean, this grows in the dimension. Of course, we want a small probability. I mean, otherwise this is not very useful. So I mean, of course, this is a term which makes things small. And this should make it smaller than those guys make the exponential growth big. So this tells us essentially how we have to choose alpha compared to the dimensions so that we get a meaningful estimate. And you see somehow, I mean, we have alpha squared here, and here we have n and p. So you see essentially the alpha should be of the order square root of n or p. Okay, so let me write this as, so our estimate in the end is less than 1/2, and then I have the exponential of, and I take out the minus 1 over 8, which is in front of the alpha squared, and then I have here alpha squared. This is good. But then, of course, I have here guys who want to grow in a different direction. So I write this as 24n minus 24p. Okay. Yeah. And now, I mean, this tells me how I should essentially choose the order of alpha so that I get a meaningful estimate. And let me now just put alpha essentially as the sum of the square roots of those guys and then an additional deviation. So let me write alpha as, let's say, the square root of 24, and I take here the square root of n plus the square root of p plus u. And this is the idea that this should be somehow things which are the mean, and this is the deviation from the mean. I mean, we don't really know what the mean is, but this should give us an idea of the order where the mean is going, because then deviations from this should be small. Okay, so and I'm doing this because then the alpha squared, I mean, I want to see that this guy here can be estimated against something which still grows like a square. So if I put alpha equal to this, then alpha squared is at least bigger than, okay, I mean, the square of this plus the square of this plus the square of this plus many other terms, but they are all positive. I just throw them away. So the interesting terms are u squared plus the square of 24n, square root of this, so it's 24n plus 24p. And then if I plug this in, so the alpha, so you see now that this and this goes away with this, and I'm left with the u squared. So what I get finally by this is that the probability that the norm of x is bigger than this alpha, which is 24 square root of n plus square root of p plus some u, that this is less than 1 over 2 e to the minus u squared over 8. Okay, and this tells me that deviation from this quantity by u are small. If u, of course, let's say u is 10. And 10, I mean 10 is, if this here is big, 10 is a small number. Huh? So having deviations of 10 from this quantity here is quite small. Okay, and this tells me that this here should give me the order of the averaged value. Because deviations from this are small. And of course, I mean, this is not the exact value of the averaged value, but the order is in principle okay. I mean, this 24 is just an accident. It could be some other number. But the main point is that we have here something which goes like the square root in n. Of course, I have here n and p, and they are in principle independent. But maybe you should think, let's say n is equal to p. Maybe that's the thing we are mostly interested in, where n and p are of the same size. So essentially, I have here the square root of n. So the expectation of the norm of such a matrix should be of the order square root of n, and then we have a large deviation from this. Okay, good. So this gives us at least some idea and also some precise estimate for the norm, how we can estimate it against the dimension. But still, it's not really giving us the precise value. Good. Okay, but so that's, I mean, good enough for now. And now I don't want to look more into the largest eigenvalue, but now I really want to look on all eigenvalues at the same time, and see what we know about them.